So yeah, I'm going to talk really about the preparation of the new seismic design maps that are based on both the hazard maps that Mark Peterson talked about and the Project 07 procedures that Charlie summarized. So I didn't have enough room on the first slide, but I wanted right at the beginning just to acknowledge, as Charlie did, all the people that were involved in this preparation of the design maps. That includes the USGS Hazard Mapping group, and I listed a few people there in particular that really worked a lot on the design maps. The FEMA-funded BSSC Project 07 that Charlie talked about, and Charlie had the list of all the folks. And then the third group that I was involved with through this process, the ASCE 7 Seismic Subcommittee, and within that an ad hoc committee on ground motion. And you can see some of the same names there as in the Project 07 group. So it was really an effort between many people. So I'm just going to start with sort of the end result of this preparation design maps, and that is ultimately ASCE 7 2010 and ultimately also 2012 IBC design map. And I've cheated here and used the old design map because you can't really read it much up on the screen anyway, but it's a map of this maximum considered earthquake ground motion, this one in particular for 0.2 second spectral acceleration. And most of the slides I'll show are focused on 0.2 second spectral acceleration, but we do the same thing with 1 second. And these are maps for site class B. We map site class B, and then the NEHR factors convert to other site classes. So just keep that in mind. And yeah, it's not in your slides probably, but the little sub-R was added in here, as Charlie talked about, to denote that these are now incorporates this risk targeting concept, and that is what I'll spend a lot of this presentation on. All right, so let me outline the whole presentation first. Again, the preparation of the new seismic design maps, it is a combination of two components: the hazard computed by the USGS, and by that I mean the probabilistic hazard curves that Yusuf explained at the beginning, and I'll show some more of those, the deterministic ground motion calculations that Mark Peterson talked about, and then the procedures that are developed by Project 07. And those procedures, as Charlie mentioned, they're laid out in the site-specific procedure of both ASCE 7 2010 and 2009 NEHR provisions in Chapter 21. And so this talk is going to be about preparing the new seismic design maps, but kind of at the same time, it's going to be about what are those site-specific procedures, because that's how we followed them to prepare the design maps. And also, probably pretty quickly at the end, I'll go over what Charlie mentioned at the end of his talk, a web application for these design maps that we've developed at the USGS and a few associated projects that make it easy to use this stuff, hopefully. And we certainly would appreciate feedback on that. I'll give you a URL later. So I'll start with preparation of the design maps. Again, it's consistent with the site-specific procedures, Chapter 21 of ASCE 7 2010 and the 2009 NEHR provisions. And so more specifically, it's a combination of two things, really. So probabilistic ground motions and deterministic ground motions that, again, Charlie talked about. The probabilistic ground motions in the site-specific procedure, you're given two options to how you can compute probabilistic ground motions. There's method one, which tells you you can take uniform hazard ground motions. Those are the kinds of maps that USGS produces, these hazard maps, not, again, to be distinguished from design maps that are in the building code, just hazard maps that are underlying those design maps. And you can hit them by this risk coefficient, which takes into this risk targeting into account. And I'll explain that more further. And then there's method two, which I'll actually go over first in the ensuing slides. Method two is you can just, for the probabilistic ground motions, compute risk-targeted probabilistic ground motions directly, because the new probabilistic ground motions are risk-targeted. And so I'll go over that first. Method two is probably more difficult to do than method one, and so we threw in method one in there for someone who might either want to get a first estimate or do a little bit less work there. The deterministic ground motions are similar to before in previous codes, as Charlie mentioned, and I guess in one bullet you can describe them as 84th percentile ground motions, but not less than some lower limits, which correspond to or UBC zone 4 values. So it's either not less than 1.5 times the short period Niher factor, or 0.6 times the 1 second Niher factor divided by t. So these end up being, for site class B, which is what we map for, lower limits of 1.5 G and 0.6 G. Okay? And then our MCE sub-R ground motions are the minimum of these probabilistic and deterministic ground motions. So this sort of outlines in our preparation. I'll mention briefly here, but not much later, because Charlie went over a lot, that all of these ground motions are maximum direction spectral accelerations, not geometric mean spectral accelerations, again, in this preparation of new design maps and in the new site-specific procedures. And the ground motions that you see on these maps, we computed, USGS computes these values. So I'll start with the probabilistic ground motions, and here's the pulling directly out of at least the current draft of ASCE 710 site-specific procedure, chapter 21, and specifically your section 2.1. Again, it's the same in 2009 NEHRB. And I'll read this part. The probabilistic spectral response acceleration shall be taken as the spectral response accelerations in the direction of maximum horizontal response. So that's what Charlie went over at some length. Represented by a 5% damp acceleration response spectrum. That is expected to achieve a 1% probability of collapse within a 50-year period. So the underline here is what has changed with respect to, say, ASCE 7 2005. And this last part, I summarize it as probabilistic ground motion is equal to now to risk-targeted ground motion. And so we'll go over how you compute risk-targeted ground motions. And again, there are these two methods. I start with method 2. And maybe on your side you can probably read it. I'll give you a second to actually skim through this method 2. Just take a second to do that. So I think this is probably about as little space we could write down, what we actually did as possible. But that means it's also really hard to decipher. I know even I think we read it over and over again and wonder what we were trying to say. But it's precise but very condensed. And so we'll try to go through an example that shows how to do this method 2. All right, and this is the same slide Charlie showed. It's just sort of given an overview, and then we'll get more detailed. Again, there's risk-targeted ground motions that are calculated iteratively for a reason I'll explain by combining one ground motion hazard curves, like the ones from the USGS, and in preparing the maps, we use ground motion hazard curves from the USGS. Site-specific procedure would be site-specific ground motion hazard curves. And again, those show ground motion versus you can think of it as probability of exceeding that ground motion level in 1 year. We also combine with the building fragility curves that were defined by Project 07. And the key thing here in defining these fragility curves was defining these small points that you see here, and we'll see in a blown up slide later, that the fact that the MCE level of ground shaking corresponds to a conditional probability of collapse of about 10%. So that defines this point here. We have to assume sort of a slope of this curve. It follows a log normal function, and we get a fragility curve that we use in this risk-targeted ground motion calculation procedure. The iterative nature of it comes in from the fact that this is, and I'm going to use risk-targeted ground motion here because we're trying to calculate risk-targeted ground motions for these probabilistic ground motions, and ultimately that feeds into the MCE as you showed by later combining with deterministic, but I'll focus on just risk-targeted ground motions here. These curves are a function of that risk-targeted ground motion. So that's where it becomes iterative, because we're trying to calculate the risk-targeted ground motions, but our fragility curves are a function of them. So we got to iterate until ultimately we achieve our risk target, which is also defined by Project 07. And Charlie mentioned that risk target being a probability of collapse in 50 years of 1%. Okay? And And we do this via this risk integral, which actually you can see Charlie referenced ATC 306. They have the risk integral in there, which is interesting. Again, they went through and looked at it and found, well, we get about the same thing if we look at uniform hazard ground motions versus risk targeted ground motions. That was a while back. You revisit that and you find out, oh, that can be true in a lot of places, but not everywhere. And that's why we worried about it in this case. So the risk integral, there's a probability of collapse is equal to an integration of this derivative of the fragility curve here, and then multiplied by a hazard curve. And we'll go through an example of this later. So just to put this in sort of flowchart form, the way we calculate these risk-targeted ground motions are, first we just guess what they are. Then we generate a fragility curve that's a function of the risk-targeted ground motion. And again, it's a generic fragility that's not specific to certain types of structures, but what's interesting about this fragility is that it is a function of the ground motion level that you designed for, which makes sense, right? Higher ground motions used for design result in less fragile structures. And that's a little bit different if you've heard fragilities in the realm of ASCE or loss estimation. Typically you have fragilities for a certain type of structure, and maybe for different code levels, modern codes, early codes, no codes. But these are fragilities that really are precisely a function of the ground motion level that you designed for, and that's why we can use them to figure out what level of ground motion do we need to design for. So third here is we integrate this fragility with the hazard curves to calculate risk, and then we check if, when we do that, we get a probability of collapse in 50 years that's 1%, our target. If we do, we're done. But we have to try a few times before we get there, so we go back and sort of guess again, and you can at that point guess intelligently and try to minimize the number of iterations here. So we do this location by location on our map, and I'm going to go through this calculation for a couple different locations. Specifically, and I use these two locations because they're really illustrative of why we bother to do this risk-targeted ground motion calculation. Looking at a San Francisco Bay Area location versus a Memphis metropolitan area location. And so these are hazard curves from the USGS, again showing ground motion versus probability of exceeding that ground motion in about 1 year. The red curve for San Francisco and the blue for Memphis. A couple things to note, and this is probably the last time, well, maybe not, the last time I'll mention this maximum direction spectral accelerations, but the USGS creates hazard curves that are for geometric mean spectral acceleration, as Charlie explained. And so we take our hazard curves and we adjust them by these factors of 1.1 for a 2.2 second hazard curve and 1.3 for a 1 second hazard curve to get hazard curves that are for this maximum direction of shaking. So, and again, these plots here, this whole example will just be for the 0.2 second spectral acceleration, but we do this exactly the same for 1 second spectral acceleration. The other thing to note here is that uniform hazard ground motion or uniform hazard maps like the one that USGS primarily produces and puts up on its website, they're interpolated from these hazard curves. So like the 2,500 year ground motions, you go over to a return period or annual probability that corresponds to this 2,500 year return period, and you get off your ground motions as Yusuf explained. So I just mentioned that because it comes up a little later. So there's the hazard curve component of the risk-targeted ground motion calculation, and then the generic fragility curve component of it. And in this sort of first iteration of the calculation, in this example, we're going to assume that the risk-targeted ground motions are equal to the 2,500 year uniform hazard ground motions. So that's a place to start. And so for the San Francisco location, that 2,500 year ground motion is about 1.3 G and about 1.2 G in this Memphis location. And so since those are pretty similar ground motions, if you were to design for those ground motions, you'd get pretty similar generic fragility curves. And so these are the two fragility curves for those two different risk-targeted ground motions used for design, but they're obviously very similar in this case. And this is one of the things that people in Memphis complain a lot about. So here I just have the equation on the right for these fragility curves. Again, the key thing to note is that they're a function of the risk targeted ground motion that we're trying to calculate and therefore need to iterate on. So we have the hazard curves from USGS over here on the right side of the risk integral. The fragility, generic fragility curve that I just showed on the previous slide, which again is a function of the risk targeted ground motion. And we can compute risk through this risk integration. And so I'll show this sort of graphically here. This top level here shows the hazard curves again, that we showed earlier for San Francisco and Memphis here. So it's this part of the risk integral. This middle part shows actually the derivative of the fragility curve. So it looks, instead of looking sort of like a cumulative distribution function in probability, it looks more like a probability density function or bell curve. There's a derivative of that, but again, these generic fragility, derivative of fragility curves are functions of the risk targeted ground motions, which in our first iteration here we're assuming are 1.3 and 1.2, and so they're pretty similar. And then you basically just point by point here, you multiply the two values in these curves, and you get this bottom curve here, and then you sum the area underneath it in the integral, and you get a 1.2% in 50 years probability of collapse for the San Francisco location, and a 0.7% in 50 years probability of collapse for the Memphis location. So we've gone through performing this risk integration. We found out that our risk in San Francisco is higher than our risk in Memphis if we design for a risk targeted ground motion that is equal to the 2,500-year ground motion, the uniform hazard ground motion. And so this risk level is what we want to have be the same in the two locations. And that doesn't seem like much of a difference. I mean, they both round to 1% in 50 years. But in the ensuing slides, we can go and say, okay, well, what if we want them to be exactly equal? How much does that change the risk-targeted ground motion? That is the ground motion that we ultimately want to use for design. And so, and let's keep in mind here that if our risk-targeted ground motion is 1.3 and 1.2 for San Francisco and Memphis, respectively, we have these two probabilities of collapse that are not equal. And so we know we want to, if we want a target probability of collapse in 50 years of 1%, which is what Charlie explained is our goal, we know we need to drop the risk in San Francisco and we can higher the risk in Memphis. And by doing that, dropping the risk in San Francisco means that we probably need to bump up our ground motions a little bit, ground motions that we use for design. Allowing our risk to get higher in Memphis means, well, we can actually drop our design ground motions, our risk-targeted ground motions a little bit in Memphis. So let's try, in this next one, risk-targeted ground motions of 1.5 in San Francisco and 0.9 in Memphis. All right, so we raised San Francisco and dropped Memphis a little bit. And you go through the same risk integration, and we find out now that San Francisco, we have a 0.8% in 50-year probability of collapse. Memphis, we have a 1.1% in 50-year probability of collapse. So we're still not quite there, but we can do this over and over again. And finally, we find that if we set the risk-targeted ground motion, the ground motion we will use for design, right now, sort of ignoring the deterministic ground motion part that we'll come to later. But if we use 1.38 for design in San Francisco and 0.96 for design in Memphis, we get, in both places, a 1% chance of collapse in 50 years. We get equal risk. And so that's what we're going through in this risk-targeted ground motion calculation. This is two locations, but we can do this calculation for every point on a grid that covers the US, and you get a map of risk-targeted ground motions for design that looks like this. This map, make a note here, it's an intermediate map, right? Because we still need the deterministic ground motion part. This is just the probabilistic risk-targeted part. So this is an intermediate map, and this map is not actually, you can't physically see this map in ASCE 7 2010 or in 2000 NEHRP, but it's a map that we actually calculate in the process of calculating new design MCEs of our ground motion map. So I show it here, again, as an intermediate step. And this is what, again, you would do if you were following the site-specific procedure as well. You would calculate this risk-targeted ground motion, and this would serve as the probabilistic ground motions part of getting design ground motions. So quickly, I'll go through, again, this is still a similar slide showing this section that focuses on the probabilistic ground motions, the site-specific section. And as we saw before, the probabilistic ground motions are risk-targeted ground motions. And now I'll just mention that we have this other method. I showed method 2 first, which was you just calculate risk-targeted ground motions. And I went through the example of how we do that. But method 1, to sort of summarize what is stated here, says, well, instead of directly calculating risk-targeted ground motions and going through all that iterative integration, we'll let users calculate uniform hazard 2,500-year ground motions, which is typically what's been done, what was commonly done in the last versions of the code, ASCE 7/2005, for example. And then we'll give them what we call a risk coefficient that they can apply to those uniform hazard ground motions. And when we do that for the map, that gets us back to our risk-targeted ground motions. You're allowed to use these risk coefficients for your site-specific procedure, acknowledging that they're sort of approximations for your site. You're not really calculating your risk-targeted ground motion. You're saying, I'll use the risk coefficients that the USGS computed, and I'll use my uniform hazard ground motions and use that as approximation. Right. So this is just breaking things up, saying risk-targeted ground motions, they can be presented as, just for convenience sake, uniform hazard ground motions times a risk coefficient, where the uniform hazard are these 2,500-year ground motions. So it's just another way to show them that's convenient, so you can kind of relate it back to these uniform hazard ground motions that we're typically dealing with. So as I showed in an earlier slide, and Yusuf also went over, that the conventional uniform hazards, say 2,500-year ground motions, they're interpolated from the hazard curves that we get from USGS, but in a site-specific procedure would be done for your particular site. And we define the risk coefficients as the ratio of a risk-targeted ground motion to this uniform hazard ground motion. And so for our example that we showed it, San Francisco Bay Area versus the Memphis metropolitan area, we calculated in the end that if we wanted a 1% chance of collapse in 50-year risk target, that we needed a 1.38 ground motion for design, risk-targeted ground motion in San Francisco, and 0.96 in Memphis. If we just get uniform hazard ground motions of the 2,500-year ground motions, these were actually the values we started that iterative procedure with. There's 1.29 and 1.18 for the two cities. And so the risk coefficient here is 1.07 for San Francisco and Memphis. The risk coefficient is 0.82. So that's saying that compared to uniform hazard ground motions in San Francisco, we had to bump those up a little bit, 7%, not much. We had to bump them up a little bit to get a risk-targeted ground motion that achieves this 1% in 50-year collapse probability goal. But in Memphis, we could drop down the risk-targeted, drop down the design ground motion to achieve this risk target. And what the underlying reason here is we saw the hazard curves for the two locations. They were different in shape, and Charlie showed those examples too, central and eastern US versus western US. They have different shapes of hazard curves, and that's what really causes this difference in the two locations in terms of how we would adjust 2,500-year ground motions in order to get risk-targeted ground motions. So that's the cause of these risk coefficients. So we can plot the risk coefficient. Maps do it for all locations like we have for these two cities. And these intermediate maps, they actually are included both in ASCE 7/2010 because they're included there so you can use them for a site-specific procedure. If you want to calculate your own risk-targeted ground motions, you can use our risk coefficients in your own uniform hazard ground motions. And they're also in the 2009 NEHR provisions because, as Charlie explained in that document, they've sort of broken down how we build up these new design maps. And so they show the risk coefficients, they show uniform hazard ground motions. They show deterministic ground motions that I'll come to now, all separately in NEHRP. So in case you're wondering, we showed this San Francisco versus Memphis gave an idea of these numbers, but this is just the risk coefficient map plotted in color. And then here I'm just showing the places where the risk coefficient is less than 0.85. So where the risk coefficient says you can design for lower than 2,500 year ground motions to achieve a 1% chance of collapse in 50 years. And the main areas are around Memphis in the New Madrid seismic zone, so that's why I choose that location. Around Charleston, South Carolina. There's also a bit around coastal Oregon where the risk coefficients are less than 0.085. And then, the San Francisco location that I used, and as well as Seattle, they're not less than 0.85. And then I'll show in the next map the locations where the risk coefficient is greater than 1.15. So there's only a few very small locations. Happens to be Sacramento, and then this area around Colorado where the design ground motions are really low anyway. So it's maybe a big factor on a small number. So most everything else is, within 15% of a risk coefficient of 1. So not a big change, and that includes San Francisco and Seattle here. So Charlie mentioned it doesn't have a big, these risk targeted ground motions doesn't change things a lot in most of the country, but it does in Charleston, Memphis, and coastal Oregon. So just to summarize the probabilistic ground motion part, and then I'll go over the deterministic ground motion. Probabilistic ground motions are now risk-targeted ground motions. The risk-targeted ground motions, they're calculated by using the ground motion hazard curves from USGS, and I'll quickly note that one advantage there, we use the entire hazard curve there. We don't just take one part of it. We use the whole hazard curve in that risk integration that I showed you, right? We have building fragility curves, a generic building fragility curve that's defined by Project 07, and then a risk target from Project 07. And then for convenience sake, we define these risk coefficients. And the risk coefficient maps are in ASCE 7 2010, as well as NEHRP, to use for a site-specific procedure. So the deterministic ground motions, what they are, the only really difference there that's underlining in the text is that now we've gone to maximum direction response, and so we have to apply factors there as Charlie described. And we're still defining things as 84th percentile ground motion, but how we do that has changed a little bit, and I'll go over that quickly. So deterministic ground motions, they have this lower floor that I mentioned before. So they're the max of 84th percentile ground motions and these lower floors. And like the probabilistic ground motions, these are for max directions. And so what we get, the USGS calculates is essentially median ground motion, deterministic ground motions, and Mark went over how we do that. And then what we do for the Project 07 procedures and for the design maps to those is we take the median ground motions that the USGS produces, we multiply them by the factor of 1.8 that Charlie explained and Yusuf pointed at as well, to get approximation of 84th percentile ground motions. And then to convert to maximum direction ground motions, we use this factor of 1.1 for 0.2 seconds spectral acceleration and 1.3 for 1 second spectral acceleration. So this is how we finally get at our deterministic ground motions that we map for design purposes. And so this just summarizes that in the end we're applying a factor of 1.1 and 1.8 to the median ground motions, and we're taking a floor of 1.5 G for site class B for 0.2 seconds, and then similar for 1 second spectral acceleration. So this is a map that shows the deterministic ground motions for 0.2 second spectral acceleration, and most of it is gray because most of it is the floor of 1.5 G, and then where the 84th percentile ground motions pop above that floor is where you start to see some of these contours. So about around faults, especially large faults in California, but also throughout the Intermountain West. All right. And these intermediate maps they're not in ASCE 7 2010, but again, they're in the 2009 NEHRP provisions because they just have a lot more. They have the details of what we did in NEHRP. All right. And finally, to get MCE sub R ground motions, there's, again, the site-specific procedure tells you you take the lesser of your probabilistic and deterministic ground motions. And that's what we did, again, in developing these design maps. So we had the probabilistic ground motions, which recall were risk-targeted ground motions. We have the deterministic ground motions, which are 84th percentile, but they have this lower limit, this floor of 1.5 G or 0.6 G for site class B. And all these ground motions are for the maximum direction. And so this is sort of the summary slide that shows that we're essentially computing probabilistic ground motions in the site-specific procedure and a corresponding map, a risk-targeted ground motion map, as we develop these new design maps. Deterministic ground motions and a corresponding map. We take the minimum of these location by location, and we get a new maximum considered earthquake sub-R, or risk-targeted maximum considered earthquake ground motion map for design purposes. And then just for sort of convenience to relate back to conventional uniform hazard maps, this one you can split, this risk-targeted ground motion map, you can split up in a uniform hazard map and a risk coefficient map. And so what's in ASCE 710 are these two maps shown, the green box here, and the risk coefficients just for the site-specific procedure, and this final map for use by engineer who's just mostly interested in the design values, the final design values, not necessarily their derivation. And then in NEHRP, we have these three maps that are shown in tan here to sort of show how we derive both risk-targeted ground motions and deterministic ground motions, and combining, and those are combined via equations in 2009 NEHRP to get this final map, which is not shown in the 2009 NEHRP provisions. So it's, again, simpler in ASCE 7 2010. So with the few minutes I have left, I just wanted to show a few of the web applications that we're developing that would deliver these new design maps and their values to the users. Here's a URL that I probably didn't have in the slide, so you might want to take note of that. It's earthquake.usgs.gov/designmaps/US-app. And right now, this is a password-protected site, and I'll give you my email at the end, and just email if you want to use it. We welcome the feedback. It's still password-protected because we welcome the feedback before we turn this loose on everyone. So please do email me for it. It's a new tool that interfaces with Google Maps where you can enter, we have the options of either 2010 ASCE 7 or 2009 NEHRP provisions. You can choose your site soil class here, enter an address or a latitude and longitude. Now we use Google's geocoding, so you don't have to necessarily get the latitude and longitude yourself. And then it shows your location on a map here. And sorry, don't have time and don't have internet here to kind of show this to you live, but here are just some screenshots. And then when you compute values here, you end up with a report that sort of summarizes both a summary report, and this is shown here, and a detailed report that gives you back all the ground motion values you need to. Ultimately, here it gives you your S sub DS and S sub D1, the design values that you need, and design response spectrum, MCER response spectrum, and the summary report. And then in the more detailed report, it shows the calculations that were performed to do this, say like the site coefficient amplification factors. Those are shown in the detailed report. All right. And then another thing that we're developing are posters of design ground motions and also seismic design categories for those who are interested in that important issue of how seismic design categories change. These design maps, they're for different site classes. The ones we put in the building code are only for site class B, but we're developing some maps that interface with Google for the other site classes and also for the occupancy categories. And these are intended to serve sort of as a check of the web application. You can use the web application, get a value, look at this poster. Either you can download or print a poster size version of it, or I'll show you in a second, look at it through Google Earth or Google Maps and sort of cross-check what you get out of the web application just to make sure that it looks reasonable. We're doing we're being really careful with the QA on our web application. And again, another reason why we kept it password protected for a while longer. But you know, it doesn't hurt to sort of have this confirmation yourself. And we have these Google Earth, and ultimately we're trying to get them into Google Maps as well. But Google Earth versions of these maps that show, this is an example for S sub DS values, design values for 0.2 second, and then corresponding seismic design categories by the color. And the neat things, you can zoom around, of course, in Google Earth and look up both your seismic design category and, you know, with some contouring, find whether this matches, you know, what you got out of the web application. And I mentioned we're working towards international building code, as Charlie mentioned, but we're also prepared a map for the international residential code that's consistent with all these numbers. And so I showed that map here, color form. I think in IRC, this is printed as a black and white map, but now this international residential code will be, residential code map will be consistent with ASCE 7 2010, so we sort of developed that. And we have, for this web application, we have some other plans for a risk coefficient calculator, so you can enter a hazard curve in it, and it would do the risk coefficient calculation for you. We haven't done that yet, and that'll take some work, but we have some plans there, and there may be others that do that as well. Adding things like long period, transition period, peak ground acceleration values, and seismic design category in the web application, which we didn't have before in our Java ground motion parameter calculator that some of you may have used, but we want to add those in the new web application. So I think I'll summarize quickly here that we've developed, you know, for ASCE 7 2010 new MCE ground motion maps that are a combination of these maps that are shown in the NEHR provisions that show things like risk coefficients and uniform hazard maps and deterministic maps, but they're all put together in ASCE 7 2010 for a new MCE sub R value that can be used directly. We also have the risk coefficient maps in ASCE 7 2010 for the site-specific procedure, specifically method 1. And then in the 2009 NEHRP, we have these uniform hazard maps, the 2500-year maps, deterministic maps, risk coefficient maps. So you can see the underlying values, go through the equation, see how they're put together, and again, they should, and they do match exactly what you would get out of the ASCE 7 2010 design values at the end of the day. And we've prepared these for these web applications that include ASCE 7 2010, 2009 NEHRP, accept addresses instead of lat-lons, well, both addresses and lat-lons, interface with Google Maps, and they give you reports on design ground motions that you can just print out and sort of use as a report on maybe in your design documents. And then as well as we've also prepared these new design maps for cross-checking purposes that are in poster form and both in Google Earth and Google Maps forms. So here's my email address and phone number. Either one is fine if you want to get the password to the web app, and we appreciate the feedback. And once we get that and incorporate that, then we'll release this publicly. Thanks very much.